Howdy everyone, welcome back for chapter 3 with chemical reactions and stoichiometry. Again, these are topics that should have been covered in both Chem 1 and Chem 2, but we're going to review them to make sure we're on the same page. So this chapter will be pretty quick since it is mostly review, but it's very important. A lot of the calculations we're going to have to do in this class are based on stoichiometry, so it's one that should be easy, but it's important to get right because everything else is going to be kind of dependent on it. So if we start out with, where does this all come from? We say, well, what's stoichiometry? It's the study that examines quantities of substances in chemical reactions. And it's all based on the law of conservation of mass from Antoine Lavoisier in 1789. And usually we simplify it to just matter cannot be created or destroyed in a chemical reaction. But just for one time, we'll get the nice translation here. We may lay it down as an incontestable axiom that in the operation of art and nature, nothing is created. An equal amount of matter exists both before and after the experiment. Upon this principle, the whole art of performing chemical experiments depends, which just sounds much more impressive. And so I think every so often it's good to, let's go back to the real primary source and say, what did they really say? Well, because we just don't say axioms enough and, upon this principle. It's good writing. It's good writing. All right, so let's use that writing. Let's say, okay, well, chemical reactions, if we can't create matter, if nothing's destroyed, how do we do this? Well, we write it with chemical reactions to show where these chemicals are starting from and going to. The arrows separate the reactants and products. We have plus signs that separate multiple chemicals, depending which side they're on, but it's just saying, okay, we got hydrogen and oxygen somehow mixed together before the reaction starts, and then they'll go ahead and react, and they'll form some water. All right? But we need to balance this because the law of conservation of mass says we can't create, we can't destroy. So how do we show that when maybe the numbers don't work out? So the hints that they'll give us here are start with an element, ideally that's only in one reactant and one product, so that if you can make those match, well, maybe it's not the right numbers at the end, but it's at least the right ratio it has to be for that element. We balance it by changing coefficients, not by changing subscripts. So we don't write a little one afterwards. We don't have to write a 1 in front. It's assumed. But we have to do that to make sure it's good. And then we'll move on to other elements. So here they did that. They looked at this carbon. There was one of them here. They looked at this carbon. There's one of them there. Well, that's equal, so carbon can be left at 1. Then looked at the oxygen where there were 2 of them here. But on the product side, there were 3 of them. So we say, well, how do we make that work? Well, let's get them both to 4. Put a 2 in front here to make it 4 oxygen atoms. Put a 2 here, so it's 2 plus 2 equals 4. And then, like they said, go ahead, double check at the end. Balancing is one thing that you should never get wrong, because as long as you can count by whole numbers, you should be able to say, yes, all of these that I start with equal all of these that I end with. And so we know that we're right. All right, why do we make sure it's coefficients? Well, because if you have a different subscript, you've changed your chemical to something else, a different chemical with different properties, different identities. So 2H2O means 2 water molecules. H2O2 means hydrogen peroxide, and there's the silly joke about, oh, I'll have H2O2 and then that chemist dies. Yeah, but the idea is, yeah, we don't want to confuse these two. They are 2 completely different chemicals. This 2 in front here with the water applies to everything, 2 separate waters. This 2 in the back here would only apply to the oxygen. So we got to make sure we do it correctly. All right. Other symbols that you might see if we're writing out full balanced reactions, you see that there's all these G's here after each chemical. That's for state of matter. We write that in parentheses after the chemical. So G stands for gas. All of these are gases. L is a pure liquid, meaning it's a liquid in and of itself. S is solid. And then AQ is aqueous, meaning it dissolves in water. So it's not a liquid by itself. It's just got dissolved to make the reaction better. You'll also notice that there's this triangle up top here. Sometimes we throw in some other symbols. So that triangle is actually a Greek delta. It's a capital delta. And that always means that heat was needed for this reaction to go. So you take methane plus some oxygen, add a little bit of heat, maybe the flame, maybe a spark. Oh, and then it will react to make carbon dioxide and water. So in this case, it's kind of the activation energy. If we have a catalyst in a reaction, the catalyst would also go above the arrow. And we'll just take this time to remember, heat is not a chemical. Heat is not a catalyst. two separate things. They both go on top of the arrow, but heat is not a catalyst. Please do not write that in a lab report ever. All right. Some simple patterns. There's different types of reactions. Some of these, or most of these, we looked at in Chem 1. There are some others that we'll get to in later chapters. But for just this first chapter, we're going to look at combination, which is also called synthesis. We have decomposition, and we have combustion. All right. So in a combination or synthesis reaction, we're going to take two or more substances, and they're going to combine to make one product. So looking at the first part of table 3.1 from the book, our general form is chemical A plus chemical B makes chemical C. It could be something as simple as two elements combined to make one compound. So here's an element plus an element makes a compound. It doesn't matter what the balancing is. We have one chemical plus one other chemical makes one product. But it could also get a little more complicated. We could have compound plus compound goes to one compound. The key is it's a single product. Whether it's an element or a compound in the reactant side doesn't matter as long as it only makes one chemical as the product. All right. So if you're trying to predict, well, what's that product going to be? If your reactants are a metal and a nonmetal, then you should be able to predict that easily. And we did this in Chem 2, where we say, hey, wait a minute, a metal and a nonmetal, that's going to combine to form an ionic compound. I know charges for ionic compounds. I can say, oh, this is +1, that's -2. I know how to crisscross the charges. I can figure out my formula. So here they say, oh, well, magnesium plus oxygen. Well, magnesium is usually a +2. Oxide is usually -2. If I switch those, oh, MgO. You should be able to predict that on your own. The only ones you can't predict are if you have something like this. It may be a little tough to figure out. If it's a compound plus another compound, how does it combine? You might have a good shot at it, but it can be tricky sometimes. But the ones that are more tricky are the ones where you don't know the group charges. So if you have a transition metal involved where it has multiple chances, like iron can be +2 or +3, which one is it? Well, that one it's really tough to predict at this level of knowledge. All right, moving on. Decomposition reactions. So they're the opposite of combination. It's when one substance is the reactant and it breaks down into two or more. So here they've just written it backwards. C goes to A plus B. And it could be something as simple as going from a compound here. Actually, all of these are about the same. One compound goes to another compound plus an element. Compound to compound plus compound. Same here. It could go from compound to two elements. That's a little more rare. Because it takes a whole lot of energy to decompose a simple binary ionic compound, but it could happen. If you just had something like sodium chloride goes to, well, then you say sodium plus chlorine. But these are what we often call special decomposition reactions, so we'll talk about them here in turn. This first one, they mentioned here, actually it's the second one here with the lead carbonate. Metal carbonates, when heated, will always give off carbon dioxide and the metal oxide. So here that's okay. Calcium carbonate, there's my carbonate. If I heat it up, I'm going to get the metal oxide, which is calcium oxide, and then carbon dioxide. So there it is, CO2. And that's just what it is. It's 1 goes to 1 plus 1. That's nice because carbonate is a -2 charge, oxide's -2, so the balancing is always 1 to 1 to 1. These other two are also examples of what we call special decomposition. This one here is a metal chlorate, right? ClO3 is chlorate. It always decomposes into the metal chloride, so here from potassium chlorate to potassium chloride. Plus elemental oxygen, so O2. That one you do have to balance because oxygen's a diatomic, so it will get you some weird things there. But again, because chlorate is -1 and chloride is -1, at least those two numbers will always be the same. And then the final one that we call special decomposition is what happens if you have a hydroxide. Like in this case, we have copper hydroxide. It always decomposes into the metal oxide. So again, just like here, the carbonate went to metal oxide. Here we have copper hydroxide goes to copper oxide. And then the other product is water. And so this one, hydroxide is -1, but oxide's -2. So there might be some balancing issues going on here. It depends on what your metal is. Here, because this copper was +2, it worked out, but if it's a +1 or +3, it won't go so nicely. But those are the three forms of what we call special decomposition. So they only wrote out the one on that next slide, but go ahead, pause this and look at those patterns again. Chlorate to chloride, carbonate to oxide, hydroxide to oxide plus water. Just make sure you know those general patterns because they do come up as we go on. All right, now let's talk about combustion reactions. These are rapid reactions that produce a flame. Sometimes if we have what's called an oxidation reaction, that's also combustion. That one can go a bit slower. We try to limit combustion to the ones that we actually see the flame and that it is a pretty quick one. It's almost always oxygen in the air is one of the reactants. So we have some fuel source, in this case propane, oxygen's in the air around it, and when you get enough activation energy to start it, there is our flame. When you burn compounds with carbon and hydrogen, what we call a hydrocarbon, we always get carbon dioxide and water as a product. So here's that propane plus oxygen goes to CO2 and water. And so they're showing, oh yeah, we'll have the fuel go in, mixes with some oxygen. I wish they would draw it a little bit there because that's what that where the oxygen goes in. If you remember these types of Bunsen burner, you turn this central cylinder in order to raise up the amount of air that gets in. But they go in the bottom, and when they come out the top, they're combined so they can burn together and make the CO2 and the water. All right, and so that's all that this reaction is about. It'll come up a little bit later in this chapter how we can use the fact that it's always carbon dioxide and water to our advantage for some other techniques. All right, now we're going to talk about the numbers part. Now that we know a little bit more about what types of reactions we're going to see, let's talk about the numbers that we're going to use with them. So the formula weight is the sum of atomic weights for atoms in a chemical formula. Remember, the atomic weight was the average of all the isotopes in the of an atom, in nature, kind of averaged together. So formula weight just says, okay, take those averages and add them together based on our chemical formula. So for an atom, well, it's the same number. If it's ionic compound, just use your empirical formula. So sodium chloride, just use NaCl. But if it's a acid or covalent compound, something like that, just use the formula they give you. So H2SO4, okay, 2 H's, 1 sulfur, 4 oxygens. Look them up on the periodic table, add them all together. There you go. Remember, AMU means atomic mass unit. So this is for a single unit of that formula, whether it's a single atom or a single empirical formula of an ionic compound or a single molecule of this compound. That's what we use AMU for. If it isn't molecule, such as an acid or covalent, we can also call it a molecular weight. You also get a lot of textbooks that'll call it formula mass or molecular mass. They're pretty much all interchangeable. Every so often you get some chemists who are very picky about what grammar we should use for various things. I'm not going to be that picky. Excuse me. All right, so the molecular weight, again, just add them all up. It's the same as formula weight. All right, so if we look at glucose, C6H12O6, so we're going to take 6 carbons, 12 hydrogens, 6 oxygens, look them up on the periodic table, add them all together, we get about 180 atomic mass units. All right. Now, percent composition is how we can look at this a little more closely for a single atom. So it says here we can find the percent of the mass of a compound that comes from each of the elements. So we want to say, well, for instance, for that glucose, how much of it is carbon? How much of it is oxygen? How much of it is hydrogen? And so our equation for percent composition, for a percent of a given element, we say how many atoms of that element are in the compound. I'm sorry, this is a slight typo that I did not see before we started. Oh, it's an equation editor. We get some live editing here. It's the number of atoms times the atomic weight. We'll try to use the same terms that they use. There we go. So we say how many carbons are there, what's the mass of a single carbon, and then divide it by the whole thing there. Now what I want to point out there is whenever we have a percent thing, we always want to use the same general formula. So if you see a percent anywhere, what we can always break it down to make sure we're on the right track is to say, what's the part we're looking at, divide it by what's the total. So we'll see this a little bit later in this chapter as well, but anytime you get something, so percent composition, percent by mass, percent by volume, anything, percent yield, anything where it's a percent, say what is my part, what am I looking at, and then what is my total. So if you see here, O, it's how much is one atom divided by what's the total molecule. So we can move ahead here and look at that glucose example. If we did carbon, okay, well, there were 6 carbons in the formula, right? C6H12O6. Each carbon weighs 12. So we have 6 times 12 is about 72. The entire glucose, the total thing, weighed 180. So once we have that, okay, 72 divided by 180, and then times 100%, we say, oh, this molecule, glucose, is 40% carbon. All right, now if we want to look a little bit more at individual particles, we're going to look at Avogadro's number. Let me exit out of that. There we go. So we're not ever going to work with individual atoms or individual molecules. They're too small. It actually messes up our averaging because our formula weights and atomic weights are based on an average. And if we've only got one atom, well, then average doesn't work. So we use the unit of the mole. And we abbreviate it MOL, so chop off the E there, that's it. But we use this term so much it's worth it. And the definition of a mole, it's actually changed a little bit when they changed the definition of what a kilogram was, and they did some other things, but it's close enough that no one's going to care about it. We said it's the amount of particles in exactly 12 grams of the carbon-12 isotope. So if you had pure carbon-12 and we had exactly 12 grams, 12 with infinite sig figs, how many particles would be in there? And then we rounded to 3 sig figs. 6.02 times 10 to the 23rd atoms or molecules is how many particles are in 1 mole. If you need a 4th sig fig, it's 6.022, which is not a bad thing to know. And if you ever need more sig figs, look in the back cover of a chemistry textbook. It should be there. All right, so a single molecule of water would be 18.0 atomic mass units. The nice thing is if we have 1 mole, if we have 6.02 times 10 to the 23rd particles, it's the same number. So 1 mole of water is 18.0 grams. So those two numbers are the same. We just have to change our unit. All right. So then that gets us to our molar mass. How many grams are in 1 mole of a substance? It's going to be the same number. It's going to be the same idea. If something's diatomic, it's twice the atomic weight because the formula says there's 2 of them. Basically, just go with the formula, whatever it says, because the formula weight in AMU has to be the same number. All we're doing is changing the unit. So 1 mole of oxygen is 32 grams. 1 mole of water, like we said, was 18 grams. 1 mole of sodium chloride, add up those two numbers, it's about 58.4445 with their rounding. But yeah, it's just the same number, just how many grams for 1 mole. Remember that's always per 1 mole there. All right, so we can then kind of sum up these molar relationships. And so we said, okay, if we have atomic nitrogen, just N, it's 14 AMU for the formula weight. It's 14 grams per mole for the molar mass. And in 1 mole, there's 6.02 times 10 to the 23rd nitrogen atoms. But then we said, well, what about elemental nitrogen, where it's, N2 that we were used to? Well, because it's N2, now it's 28 AMUs, because there's 2 of them. We got to double it. The molar mass is 28 grams per mole. And then if we said for 1 mole, what are the particles? Well, it's still 6.02 times 10 to the 23rd molecules, because that's the whole thing together. Or we could double this and say it's 2 times 6.02 times 10 to the 23rd nitrogen atoms. So that would be, 1.204 times 10 to the 24th nitrogen atoms, because we double that number. One thing to look at for ions that's important, notice how, we've removed an electron, but they note here, the electron's almost 2,000 times smaller. It's not going to affect this decimal point. It's going to affect a decimal point somewhere out here. So we don't have to change that number at all. So whether it's silver metal or an atom of silver or an ion of silver, same numbers for all of them. And then barium chloride, one thing to watch out for here when you have a more complicated formula, again, add it up. So it's 208.2 AMU for 1 unit of it. It's 208.2 grams for 1 mole of it. And again, Avogadro's number, we say, well, based on the formula, the whole thing, there's 6.02 times 10 to the 23rd. For barium, because there's 1 barium in the formula, it's 6.02 times 10 to the 23rd. But again, for chloride, because there's 2 of them, it's 2 times Avogadro's number. So again, the 1.204 times 10 to the 24th chloride ions. So you always have to watch out for things in a formula if you're breaking it all the way down to atoms or ions. But if you're just going for molecules or formula units, it's always the 6.02. Okay. Well, now we want to use those numbers, whether it's the molar mass, the formula mass, or Avogadro's number, to convert between these. So moles provides us our bridge, and using equalities, or what we call conversion factors, we can convert from mass to atoms, excuse me, or atoms to mass. So if we just had this question, how many atoms are in 3 grams of copper? We'd take 3 grams, and so here's this conversion, that 1 mole of copper, normally I'd write the 1 mole on top, is the same thing as 63.5 grams of copper. That might just actually be an editing issue with this formatting. Because, we just said with molar mass, 1 mole of copper is 63.5 grams. That's the mass that's on the, or the atomic weight that's there on the periodic table, and we just make that grams per mole. And then you can see grams cancels out. We then have 1 mole of copper, and we said, in 1 mole of copper, there must be 6.02 times 10 to the 23rd atoms of copper. And I wish they had put copper up top there. But either way, you cancel that stuff out, and it just so happens when you're rounding to just one significant figure, that it would be 3 times 10 to the 22nd atoms of copper. But the key thing is, grams was started, so grams went on the bottom. Moles went on the top. Well, now since moles was on top here, it went on the bottom there to cancel, leaves us with atoms, which is what we want. And we could go the other direction as well. It would just flip these ratios. We also want to talk about empirical formulas. Remember that an empirical formula was the simplest whole number ratio of all the atoms in a formula. And so if we have either the grams for each element, or if we only have the percentage, if we found that from mass percent, which you often get from experiments, we can use these starting points to get that empirical formula. So our 3 steps are, if we start with percents, we're going to assume a 100 gram sample to get to grams. If they give us grams, just start here and do 2 steps. We will then use the molar mass so that we can get to the moles of each particular element. And then the 3rd step, we're going to use a mole ratio. We're going to say, if these things have to be relative to each other in whole numbers, let's use a mole ratio to figure out what that empirical formula should be. So we're going to do an example here. We have the compound para-aminobenzoic acid, which is in some sunscreens. I prefer the stuff that's just zinc oxide and titanium oxide, but yeah, this works. They did an analysis. It was 61.31% carbon, 5.14% hydrogen, 10.21% nitrogen, and 23.33% oxygen. And they want us to find that empirical formula of the para-aminobenzoic acid. So we're going to do our 3 steps. The first step was convert from percentages to grams. And so they just say, assume 100 grams. Well, then that 61.31% of carbon, we just make 61.31 grams of carbon. And the same thing for all the others. So if you pause the video and go back to the previous slide, it was 5.14%. So now it's 5.14 grams of hydrogen. And same for nitrogen, same for oxygen. Step 2 is then to convert these to moles. So because this is carbon, we use carbon's molar mass, 12.01. This is hydrogen. We use hydrogen's molar mass. Nitrogen, oxygen. Now note for these 3, those are all diatomic elements, but para-aminobenzoic acid isn't an element. It's a compound. So since this is an element in a compound, we just say, well, what is it for a single H? What is it for a single N? Because we're not trying to calculate diatomics because they're not by themselves. So make sure you keep that in mind when you're doing this. We use the atomic values for a single atom because we're looking for this single, or we're looking for the number of atoms in a compound. These are not diatomic elements here. So we do that math. We get 5.1, 5.09, 0.72, 1.46. So we just have the absolute number of moles based on that analysis. The next step is we're going to calculate a mole ratio, and we're going to divide by the smallest number of moles because that sets everything relative to 1. So when we look through those four numbers, the nitrogen at 0.7288 moles was the smallest. We divide everything by that, so it becomes equal to 1. For the others, we also divide it by 0.7288. And what we should get, or hopefully should get, are some things that are very, very close to whole numbers, like these. And some rounding is allowed. So 7.005, yeah, that's 7. 6.98, yeah, that's 7. Yeah, that's 2. Now what might happen, and they don't do any examples here in the slideshow, unfortunately, but you might get something that's like 1.5 or 2.5 or even 3.33. For those, you need to remember how do decimals and fractions kind of line up. So if you ever do this step and you get a 0.5, well, that's where you say, well, I want a whole number ratio, so I'm going to multiply everything by 2 so that the 0.5 gets doubled and becomes a whole number. If you get a 0.33 or a 0.66, that's where you say, well, 0.33 is 1/3, 0.66 is 2/3. If I multiply by 3, they'll become whole numbers. But again, multiply everything by that factor so that the ratio stays the same. Those are in your book. It's just they kind of left it out of this slideshow. So final step, we just make those numbers. We calculated the subscripts. So C7, H7, NO2. And if we want to just take a quick moment, we can draw that molecule. So it would be C, C, C. You're not expected to know this because this is organic chemistry, but if you want a slight preview of what organic chemistry might be like, you have to look at all those words and know what they mean. So the benzoic part told me, the benzoic acid, that's what this basically is. You have a benzene ring, so let's get some double bonds in there. These all have hydrogens, well, 4 of them do. The amino part tells me that there was an NH2 sticking off of this, and then the para part told me that it was opposite from the acid part, so I'm going to put it here. This one is the para position, and if we count that up, sure enough, it's C7, so 1, 2, 3, 4, 5, 6, 7, H7, 1, 2, 3, 4, 5, 6, 7, N, and then O2. So in this case, the empirical formula is the actual molecule. Again, you don't need to know that, but it's just sometimes nice if you have some extra information to double check, does this make sense? All right, for molecular formula, where we're saying what is the actual formula, what we need to know then is not just what the ratio is, which is the empirical formula, we also need to know the molar mass or molecular weight of the compound and see how it compares. So we could say, well, if the number's the same, well, the formula must be the same. But if the molar mass is double what we got for the empirical, well, then we need to double our formula or triple it or quadruple it, whatever the ratio is between the molar mass and what our empirical formula has for its mass. So for instance, say we got an empirical formula that was just CH, and then we're given extra information that the molar mass of this compound is 78. Well, what's the molecular formula? And so we'd say, well, CH, if this were our chemical, carbon is 12, hydrogen's 1, they're just rounding here. That would be 13. We say, well, what's the ratio between 78 and 13? Well, it's a 6-to-1 ratio. Oh, well, that means our empirical formula is 6 times too small. We got to make it 6 times bigger. So CH becomes C6H6. And then that weighs 78, and that would be our answer there. So it's just take the empirical and say, how do I make it, what do I have to multiply by to make it equal to this molar mass they gave me? And if they don't give you the molar mass, you can't get it. You have to get that number from somewhere. All right. Now here's one where maybe they didn't give you that number, but we can get it from somewhere. We can get it from this experiment. This is what's called a combustion analysis. So this is what I talked about earlier of using the idea that combustion always gives you water and carbon dioxide to our advantage. So say we had a chemical that was carbon, hydrogen, and oxygen, and we want to know, it's an unknown, what's the formula? How can we figure it out? So it says here, well, the mass of carbon is determined from the mass of carbon dioxide because all the carbon in the compound only goes to CO2. There's nowhere else for the carbon to go. So if we know how much CO2 is made, we can do some stoichiometry calculations and say, well, if it's this many grams of CO2, it must be this many grams of carbon. We can do the same thing with hydrogen. Any hydrogen that was in the compound must go into the water. And so once we know, well, how many grams of hydrogen are here, well, that's how many grams of hydrogen must have been there. Now, the oxygen, if there's oxygen in our unknown, is a little bit trickier because we're adding oxygen in the reactants, right? It was the hydrocarbon plus O2. So if we want to know oxygen, we can't just say, oh, what is it? What we have to say is, how much of this compound did we start with? And then what are the masses of the carbon and hydrogen that we've already figured out? So say it was a 5-gram sample. And then we do the step 1 and we say, oh, it's 3.5 grams of carbon. Got it. We do the second step and we say, oh, it's half a gram of hydrogen. Great. Well, that's 4 grams. Well, if we had a 5-gram sample and we've accounted for 4 grams of it, what's missing? We're missing 1 gram. That 1 gram must be the oxygen. So we can't determine the oxygen directly because we're adding the oxygen in. We have to determine it from these two compared to what we started with. So if they really gave you an unknown, they said, here's some real unknown, and you found out, oh, when I add my carbon and hydrogen together, it gives me the total amount that I started with, well, then you know there is no oxygen in the compound. It would equal 0. But if there's any difference, and they say, oh, it's oxygen, well, then that difference is the O there. So we'll do some examples of that in class. It is a bit tricky, but it's just keep track of carbon's got to go here, hydrogen's got to go here, oxygen must be the difference. All right, so if we break it down just a little bit more, we say, okay, we know how much CO2 is produced. We can use that molar mass to go to moles of CO2. We know that for every CO2, there's 1 carbon, so that's equal. And then if we have the moles of carbon, we can use its molar mass to get to the grams of carbon. All right. Then for hydrogen, same way. We know how much water was produced. Use its molar mass to go to moles of water. We can say, oh, there's 2 hydrogens for every water molecule, H2O. And then say, okay, well, hydrogen is 1.01. Use that molar mass to get to grams of hydrogen. And then, so that gives us carbon, that gives us hydrogen. We can then put it together to say, is there anything missing that must be oxygen? All right. Now, once we have, say we're not doing that stuff anymore, we're not looking at unknowns. We're just looking at, I know what chemicals I'm using. I know what reaction I want to use. How can I get quantitative information out of that? When we look at those coefficients, they're giving us either the number of molecules, or we can get them as the relative number of moles. So if we have this 2 to 1 to 2, well, it could be 2 molecules and 1 molecule 2. It could be 2, 1 to 2. Or what we really want is it's saying that for every 2 whatever of hydrogen, there's 1 unit of oxygen, and that will give us 2 units of water. All right, so it's either moles or molecules. And then if we go ahead and say, oh, look at the grams here just for fun, to go back to Lavoisier, if we convert all these moles here to grams, we'll see, okay, that's 4 grams of hydrogen, that's 32 grams of oxygen, 2 moles of water would be 36 grams. Hey, 4 plus 32, well, that equals 36. So there's our conservation of matter sticking its head up again. And it's good to know that, yeah, it works. It should. Every so often in some math equations, you can use this to your advantage. If you know 2 of them, you can say, well, what's the missing number that makes the equation work? All right, so when we do stoichiometry, which I find it a little amusing, they put this slide after the combustion analysis because this 3-step here is what they did for combustion. If we know how many grams of a substance we have, we can use its molar mass to get to moles. We can then use the balancing coefficients to get to moles of another chemical, and then use its molar mass to get back to grams. So this is all stuff we did in Chem 1 and Chem 2. So, we should be very familiar with this. But that mole ratio is what the coefficients give us. So we have to make sure we get the balancing correct. Then we can do our stoichiometry correctly. So if we do an example here, it says how many grams of water can be produced from 1 gram of glucose. So we have our balanced reaction. This is, if you guys remember from biology, this is our cellular respiration, how we get energy in our bodies. So we have 1 gram of glucose. Our first step is to go from grams to moles for substance A, glucose. So we say 1 gram of glucose times its conversion factor, 1 mole of glucose over 180 grams of glucose. And they show us that the units are canceling nicely. Now they're going to just add on each time here, so this first part's the same. But now second step, we're going from moles of substance A to moles of substance B using our coefficients. So it was 6 moles of water for every 1 mole of glucose according to the coefficients, right? If we just flip back briefly, 6 moles of water for 1 mole of glucose. So that's our 6 over 1. And now again, you see how the units cancel. Mole of glucose on top, mole of glucose on bottom, so they cancel. This is why I strongly recommend when doing stoichiometry, yes, it will take more time, but it will help keep you organized. Write out the chemical formulas so you know which one of these moles goes on bottom, which one goes on top, because the last thing you want is to accidentally flip these and divide by 6 when you're supposed to multiply by 6. All right. Last step is we want to go from that moles of substance B to grams of substance B, so in this case water. So adding on this third conversion factor, since we were in moles of water, 1 mole of water goes on the bottom. There's another typo. Discard. I thought I checked all this before I started. They had messed up Avogadro's number in an earlier one. It was very disappointing. 18. There we go. There we go. 18 grams of water for 1 mole of water. And so that will then work out. And so if we do our last step here, that's how it is. Now we do our calculation. And I like to do it this way, where you do it all as one big calculation. You can do them separately, so you could have gotten this number after the first one and then started up the second one and then start. I like to do it all at once because, in my opinion, it gives you fewer chances to accidentally flip something or mess it up if everything's kind of together. So 1 divided by 180 times 6 times 18. When you do that, you get 0.600 grams of water, and that makes sense. The answer looks reasonable for what we're doing. All right. What we can do with this then, we can also use heat in stoichiometry. So if we're told that some reaction absorbs a certain amount of heat per mole or releases a certain amount of heat per mole, we can make one of those conversions be that conversion of 500 kilojoules per mole. Now, heat isn't in the reaction. It would be given on the side as a delta H value. We'll get to that in Chapter 5. But it's just a very similar conversion that we'll see in the future. Just kind of keep it in the back of your mind for a little bit that it's coming. Talking about these reactions a little more specifically, we would prefer that when we do a reaction, everything is perfect, that we put in the exact amounts of reactants that we need so that every bit of reactant reacts and gets used up, and we get the maximum amount of product. That does not happen. A lot of times there's slightly more of one reactant or slightly less of another because of measurement. We don't want to waste our time getting the perfect amount of grams. If you need 2.5 grams, 2.45, that's excellent. Good enough. Don't waste your day trying to get 2.5000. It's not going to happen. So the limiting reactant is the reactant that's in the smallest stoichiometric amount. And that means the one that's going to run out first, the one that's going to be used up first. So here we have 10 molecules of hydrogen pictured. That's the white. And we have 7 molecules of oxygen pictured. Again, we want to practice our particle views. So if you count, the number does matter there. They're trying to show us that. So after the reaction, since hydrogen and oxygen, it's 2 hydrogens react with 1 oxygen. If we kind of pair them up, okay, these two with this oxygen, and then these two with this oxygen, and then these two with this one. If we keep doing, at the end, we'll have 10 waters, we'll have 2 oxygens left over, and we'll have no hydrogen. And in that case, because hydrogen was used up, there's none of it left, hydrogen is the limiting reactant. Oxygen, because there is a little bit left over, is the excess reagent or the excess reactant. Reagent, reactant, interchangeable. All right. So that limiting reactant is very important because since that tells you when the reaction stops, it tells you how much can we really make, how much product could we really get. And so that's why we want to do every other reactant or every other calculation based on the limiting reactant once we know what it is. So if we want to say, if we didn't count this, but we want to say, well, how much oxygen is left over, we base it off the hydrogen. If we want to know how much water could we make, we base it off the hydrogen. All right, the theoretical yield is that maximum amount that can be made. And again, it's the maximum before the limiting reactant runs out or when the limiting reactant runs out. So even though we had enough oxygen to make 4 more waters, the theoretical yield in that picture was the 10 because 10 was the most we could make before something ran out. And that's different from the actual yield, which is what we actually get. So when we do a lab, the actual yield is what we actually measure on the balance at the end or whatever. And these will be different because of, hopefully not mistakes, but maybe we didn't give it enough time. Maybe things didn't stir enough. Maybe we needed to heat it up more. Like I said with time, maybe the class period was ending, so we had to say, no, we got to stop now so we can finish the other steps. Or maybe there's side reactions where we want this one product, but there's a chance of another product being made instead. And so, we want to get this. So lots of reasons, even when you haven't really messed up yourself, or it's again, just get a better purity of your yield. But the theoretical yield is what the stoichiometry math says you should get. The actual yield is what the lab says you got. And we want to compare them with the percent yield, which again, it's a percent, which means it's part divided by total. The actual yield is the part you actually got. The theoretical yield is the total you should have gotten. And so when you divide those two and multiply them by 100, that's how we'll get our percent yield. And I believe, yes, that is the end of this chapter. We're going to do lots more examples in class, but this hopefully brought some things back to mind. If you're watching this before the semester starts, or even during, this would be a good time to go back to your Chem 1 or your Chem 2 notes. Chem 1 is going to be your basic stuff on balancing and basic stoichiometry. Chem 2 is going to have some limiting and excess reactants and percent yield stuff. So make sure you go over those so that you're a little bit more familiar with these to help you out with the practice we do in class. All right, but hope that you guys enjoyed Chapter 3.